orphan of a topic that Five had just kind of sandwiched into chapter 6, because this has no connection, not even a specious one like the previous, the matrices. It's about linear optimization. So this is when you have a series of linear constraints and you're trying to optimize an objective function, one that involves both x and y as inputs over those constraints. So like, for example, Wrestling's doing a fundraiser, selling donuts and Dr. Nuts. When donuts cost so much, the Dr. Nuts cost so much. But we got some constraints. Let's say like you only got 300 packages of donuts max to sell. You've only got like 400 Dr. Nuts to sell. So those represent some constraints. So what would be the maximum amount of money your team could make? Well, of course it would be if you sold all of them. But sometimes there's an additional constraint, like the sum of the donuts and the Dr. Nuts have to be less than 500 or something like that. So I don't know how we could explain that with a real life scenario, but additional constraints create some more interesting optimization problems. So this is an example of linear optimization. And one of the primary things we need is a formula I'm about to show you, but we'll look at this first. So optimization is when we find the best value for an objective function under constraints. And the reason I say best and not greatest or least is sometimes it's greatest, sometimes it's least. If it's a negative thing, we want the least of it possible. Like, I don't know, losses for our business. We want to minimize those. Sometimes we want to maximize a thing, if it's profits, for example. So the best value may be the greatest or it may be the least. And it will vary by circumstance. An objective function is a function in multiple variables that we need to optimize. And then constraints are inequalities that constrain the parameters in an optimization problem. Like my example for Holden, you've only got so many donuts to sell, or whatever. And then the feasible solution are vertices of the solution area. So in other words, the edges, where the edges come together, the vertices. If you're a person that likes graphs, you're going to love this little section. It's fun. Always like graphs. It's the maximum pour rate of this carafe without spilling. Look at that slide. So the formula I referred to is the Vertex theorem for optimization. So if this is the solution area, the maximized and minimized objective function must fall on one of the vertices, A, B, C, D, E, or F. So when I'm trying to maximize or minimize a function, the maximums and the mins must occur at a vertex. So no matter what the constraints are, it has to be at the vertex. So the optimal value occurs at the vertices. So step 1, graph the region corresponding to the solution of the system of constraints, find the coordinates of the vertices, plug those into our objective function, and see which one is the highest or lowest, whichever we're searching for. Okay. So I find an interesting one here. I think this one probably best. So we'll use a graph here. positively obnoxious to have your default text persist in that case. Horrendous program. So we're going to graph each of the constraints. Wow. That is just determined to stay, isn't it? We're going to graph each of our constraints. And in order to graph them, we need to move them into slope-intercept form, graph the boundary equation, and then use a test point to determine which side to shade. So I've got 2x plus 3y equal to 12. That is the boundary of that inequality. And it will be a solid line. Everything's solid in this case. So I just changed the inequality to an equal sign, and that represents the boundary, the edge of that inequality. And that's what we're going to graph first. So let's move this to standard form. So I've got 3y equals negative 2x plus 12. And if I divide both sides by 3, I get y equals negative 2 over 3x plus 4. So this is the boundary and slope intercept form. So tell me what my y-intercept is here, Grace. Say again. Okay, so with linear equations, which is y equals mx plus b, remember that the y-intercept is the b value. It's okay, 4 is what I'm looking for. 1, 2, 3, 4. So 4 is our y-intercept. Tell me what my slope is, Rachel. Very good. So if I know the slope's negative 2 over 3, Ian, how can I find my next point? Very good. Down 2 over 3. Down 2 over 3. See how this works? And then if I'm going this way, I go back 3 up 2. And again, it is a solid line there. And if your points don't line up, you did something wrong. And mine don't line up perfectly. They don't line up at least a little bit, you did something wrong. There we go. So there's the first boundary of the inequality. Now we're going to choose a test point. In other words, it's either this side or that side. Do you see what I mean? That satisfies the inequality. We're going to pick a point in one of those regions and test it to see which one satisfies the inequality. In other words, makes it true. So the origin is always your best choice. The only reason you couldn't, well, it's not always, it's almost always your best choice. The only reason you couldn't choose the origin is if the boundary ran through it. So as long as the origin's not on the boundary, we'll choose that. So let's plug in 0, 0 here. Is 2 times 0 plus 3 times 0 less than or equal to 12? Yeah, so we know this is the solution side because this test point satisfies the inequality. It's like flipping a coin, and I'm going to say it's heads, so it's heads. Or I can say, if our test point fails, I can say it's not tails. Either way, it's heads. See what I'm saying? So the test point proving true or false will tell us which side it is. It's either going to include a side or exclude a side, in which case you would know it would be the other. In this case, it included. So this part's kind of tedious, and I know I've got some OCD people about symmetry because this is an advanced math class. And we really, we can save ourselves some grief here. So before I do that, let me take a look at these last two. You see how this confines us to Q1? So we don't even really have to worry about these two. That just means we're only talking about Q1. Because X has to be greater than or equal to 0. Y has to be greater than or equal to 0, which means X and Y are also part of our boundaries. And so we're only talking about Q1. So we really don't have to worry about shading outside of that. So I'll just forego that. And I'll make it a little smaller. I think I have to do that over. No, there we go. That's a small one. So we've shaded the appropriate region for the first constraint. Now let's do the second constraint. So this time we're worried about 2x plus y equals 6, which is the boundary of that second. I say y equals negative 2x plus 6. There's no coefficient of y to divide away this time, so I just have it like this. So tell me what my y-intercept is in this case, Kristen.
6.
Very good. So right here. And then tell me what my slope is in this case, Rowdy.
-2.
Good. So how would I find my next point?
You would go to the right and down 1.
Well, not down 1.
Down 2, sorry.
Down 2, right. So right 1, down 2. Right 1, down 2. So now, our feasible region is now defined. And we need to test the point. I'm pretty sure 0, 0 is going to pass. 0, 2 times 0 plus 0 is less than or equal to 6. True. Which means our solution is going to be right in there. So we need the boundaries of that, or the edges coming together into vertices. We need those vertices. We use a different color pen because that's too much red going on there. So here's one, here's one, here's one, and here's one. Those are all vertices of the solution area. So first one is 0, 0. And we want to plug these into the objective function f up here. So we want to find f of 0, 0. And then out here, I've got 1, 2, 3, 3, comma 0. Just double checking if that's right. Yeah, 2 times 3 plus 0 is 6. So there's another one. And then I've got this one, which is 0, 0, 4. And then finally, we might have to do a little algebra here. We want to know where this intersection occurs. It looks like it occurs at 1, 3, but let's put them in our calculator just to make sure. So if I go negative 2x plus 6, and then I go negative 2/3 x plus 4. I think that's right. And I zoom 6, which gives me the standard window, what we see here. Yep, so this is point of intersection is what we're concerned about. Everybody. And we see it's 1.5, comma 3. Okay, so what we've done is graph all the constraints, find the area that represents our solution, and then pick the vertices from that area. That makes sense to everybody? Vertices of the solution area is where I got these numbers. Now I'm going to plug these into this objective function. So this is also part of the problem. So we'll just use that as a guide here. And I've got 0x plus 3 times 0 equals 0. So f of 0, 0 is 0. And let's see what they want us to do here. Find the maximum and minimum values, okay? And then I've got 3 plus 3 times 0 equals 3. I've got 0 plus 3 times 4 equals 12. And I've got 1.5 plus 3 times 3. So that's 9 plus 1.5 is 10.5. So this is my min. This is my max. It's a little too crazy with that. So maximizing or minimizing an objective function with constraints. Linear optimization. Questions about that one? Okay, so I think I gave you one homework problem for that. Let me go ahead and put it up here on the board.